Bueno, buenos días a todas y todos. Muchas gracias por estar aquí. Hello, everyone, and welcome to this new INRIA Chile talk. So I'm Julia, Director of Partnerships and International Relations at INRIA Chile. And I'm very happy today to welcome Xavier Hinault, researcher at INRIA in Bordeaux in France. So I will shortly introduce Xavier before letting him take the floor. So Xavier is researcher in bio-inspired machine learning and computational neurosciences at INRIA in Bordeaux since 2016. He received a master and engineering degree from Université Technologique de Compiègne in France in 2008, and a master in cognitive science and AI from École pratique des hautes études in France as well, and then his PhD in Université de Lyon in 2013. So his work is at the frontier of neurosciences, machine learning, robotics, and linguistics. And with no further introduction, Xavier, I will let you the floor. Thank you. So,
thank you very much.
Okay.
Now, you hear me? See? Okay. So thank you very much for the kind introduction. So I will present you part of my work, and in particular my last project called BrainGPT, Tailoring transformers into cognitive language models. And so I work on a lot of machine learning and bio-inspired machine learning. So my aim is to try to understand the brain, how to model the brain and brain mechanism, and also how to make machine learning more efficient by taking inspiration to the brain. ¿Qué pasó? Está bloqueado. Sí. So the BrainGPT project, the idea is to bridge the gap between LLM, so large language models, and how the brain works to create neural architectures that are more efficient. So first, you're going to work, and I need someone to want to participate. Who wants to? What's it? So who wants to try to? So I will put a sentence, and someone will have to say it again. So who wants to participate? Yeah. Okay. Okay. So listen carefully.
When I talk to you, I hope you understand me well.
Can you repeat? Yes. Very good. So next one. You want to do it?
Dlaczego kapelusz miałby być przerażający?
Yeah, so now it seems much more difficult because it's the same length as the first sentence, but it's much more difficult because you don't know the language. So which is Polish. So of course, when you don't know the language, it's more difficult. And who wants to try the last one? Again, same player. So few people can do these sounds, but they are very difficult. I cannot do. So these were canaries. So here you can see the spectrogram, so the time frequency representations, and you can see that for different languages they are quite similar. It depends on the speaker, but you can see that. But for canaries, of course, you see that it's really different, and you have very different syllable, and it's more difficult for us to do it. But so the idea is, how do we make sense? How do our brain is able to learn, reproduce, and imitate all these sounds and this continuous flow? Because as you see, when it's in English, it's easy, and when it's in Polish, it's more difficult. When you don't know the language, it's much more difficult because you cannot store all this information at once because you don't know any of the hierarchical level of language. And so the idea when children learn language, they start small and they start with bootstrapping from a few shots. So for example, the first thing they learn is to learn words. So they learn, for example, to recognize an animal. So for example, in the first context, you see all these three animals and the child here, mippen. And it has to map this stream of sound, so mippen, to something. So, and of course, in continuous time. And the child sees mippen in different contexts, and so in the end, it can learn that this animal, which we would call an elephant, is a mippen in this language. And so this is this cross-situational language learning ability. So that has been shown, for example, by you and Smith, that Ethan rapidly learn word referent mapping via this cross-learning statistics. Okay, so now how are we going? So which model do exist and are able to predict the brain? So since less than 10 years, there have been a lot of work on brain encoding and decoding, especially with the transformer architecture, which is this one. So since the 2017 paper on transformers. And for example, we did a bit of brain encoding, which is more better prime because brain decoding is a bit ill-posed problem. And the idea, so you take a transformer or any machine learning algorithm and you try to predict brain activity. So it seems a bit crazy, I agree with you, but it works in part, and it works surprisingly well as far as I'm concerned. So we do brain encoding, so we take a transformer. For example, we give it a chapter of a Harry Potter book, and then we have people in fMRI scanned, and they read or they hear the same chapter of Harry Potter, and then we look at the activity synchronized in the model and in. We see, for example, so depending if we have a 4-layer, 8-layer, or 12-layer transformer model, we can see that some areas are not so bad at predicting brain activity. And actually, these are the some first results, because it's an emerging field. And several models are able to predict about, at best, 10 to 30%, depending on the studies, of brain activity. Okay, but the problem is that they don't learn the same way as we do. For example, Llama 3 was trained on 15 trillion tokens, so I'll let you count the number of zeros in this number. And so how much time would a human need to read the equivalent of 15 trillion tokens? Do you know? So it's about more than 100,000 years. So it's very long, and you have the estimation here by ChatGPT. And so how many human life would it take? More than 28,000 human lives. So definitely, Llama 3 or any large language model did not learn the same way as you did, because it learned much more things and had access to much more text, but still is not as intelligent as you. So there's a way to make this a bit more smarter, because even a 3-year-old kid can do reasoning better than a large language model and adapt to new things in the world. Okay, and what is specific to children and also to songbirds is that they have several, so these are the different stages of learning for the first year, so songbirds or children. And you see that within the first 12 months, they have a lot of different stages where they learn different things. And so we did a model actually on this sensory motor learning, but I don't have time to show it here, on songbird in particular. But what's interesting thing here is that this developmental learning is that you have several stages, and these several stages mean that at each stage you are bootstrapping with the few knowledge, the few information you have to go on top, to go to the next stage, okay? So you don't need much data to do this, because that's how it works. Okay, so can we do, how are we going to model this bootstrapping ability? And so the idea is that we just take one problem. So we try to learn only with 1,000 sentences. So that's very little. And definitely the transformer is not going to help us, because also another problem is that it makes computation that are not biologically plausible, because our brain, when I talk to you, you hear one word at a time, and that's why when you have a sentence in Polish, if you don't know Polish, you're not able to recreate it because you cannot access like a transformer all the words. And the transformer, instead, they process all words at all time. So each time you ask them a question, on Harry Potter, for example, they have to read the whole book again. It seems crazy, no? And that's the same for each word they are producing when you are talking in a conversation. That's why when you have a very long conversation, it's better to summarize it and to start a new conversation, because it takes more and more computation each time the conversation is great. Okay, so as I said, transformers have to read the book each time. It creates a word. And the problem is that there is this quadratic complexity. So the attention mechanism that you can see here, you have to compare basically all the words with all the words. So you see why it's quadratic in number of operations. And because you need to compare each word to each word on the full sentence, so the full book. And for each word, it's taking an input, or each word it's producing. So that's crazy. And it's actually quite impressive how they managed to make it efficient to run on in parallel and so on. But still, the basic mechanism is too costly. Like, we know there are some ways to do better, because our brain is able to do this on-the-fly process. Okay, and what's interesting is that our brain just used 20 watts. So just 2 light bulbs. And I don't know exactly, and we don't know all the time how much GPT is doing, but we heard that they are buying a nuclear power plant to make it work. So I guess that's not 20 watts. Okay, so how to balance performance and energy? So to have this bootstrapping and on-the-fly process, the idea is that we can use, for example, recurrent neural network, because they can process input on the fly. So you put one input at a time. They are made for this. And our brain also, there is a bit of an equivalent here, because our brain is really recurrent. So for example, it has been shown that the cortex is really recurrent. Okay, so first, maybe a bit of a reminder, what is a recurrent network and what is not a recurrent neural network. So, for example, if you give an image and you want to have an output like cat, this is a feed-forward network. Okay, so if you have so here you just have one layer, so information goes from here to here, and so you connect from one layer to another. It's to make static association, like image to cat. Now, if you have to recognize, for example, instead of an image, a video, then you need a recurrent neural network, basically, and so then the information flows around like this, and the idea is that you have dynamical memory of temporal context. So, for example, to recognize a gesture. And so these are the two models. So, of course, for the feed-forward network, you take several layers to train, and this is very efficient. And what is important here is that each input is independent of the previous one in feed-forward network, and in a recurrent network, each input is dependent of the previous one. Okay? Okay, so how do recurrent neural network could work? In the easiest way, how we could train a recurrent network in the easiest way. So, for example, we have a sentence, I hate Mondays, and we are going to put one word at a time, so to have this process on the fly inside the network. And you can see that you have a dynamical encoding of the system. And then, by the way, who says I hate Mondays? No one? so it's Garfield, and the idea is that so the most basic mechanism is called Hebbian learning. It's have been hypothesized at the end of the 40s, and how the brain could learn. So the idea is that if you have two neurons that happen to fire at the same time, probably they should be related, so you enhance their abilities. Okay, so that's what we do here. And this means that the other time we hear Garfield saying, I hate Mondays, or just someone saying, I hate Mondays, it will mostly trigger this neuron, because we reinforce the connection between this one and this one. Okay? But so now you're wondering, I just told about making this connection more strengthened, but I didn't talk about the other connections, right? And the thing is that actually the other connection don't need to be trained. They just can be random, and the process will work again. Because you just put one word at a time, you have dynamics that are proposed by the random connection, but if you put it in the same order, it will be the same dynamics, okay? And even with a random recurrent network, you can have interesting dynamics. And that's what it's called, reservoir computing. And the idea is reservoir computing, so you have this recurrent network with only the output layer, which is trained, okay? So it's a bit, at start, it's a bit strange, and you feel a bit disturbed by this, but actually it has a lot of powerful properties. And so we're actually developing a reservoir computing library called Reservoir Pi. So you can see on GitHub, and you have a lot of tutorials, and you have last versions, 0.4 version with a lot of acceleration and so on. So you can try it out. And we are one of the best, most popular reservoir computing framework because of the two engineers that we managed to have to develop the library and to have good documentation. Okay, and so this library is so easy to use that it was also used in different hackathons. So I organized several versions of the Hack One Robot hackathon. So this is at the Science Museum in the Fab Lab in Cap Science. So you see different kind of project. And some people use Reservoir Pi to make a crazy dream to become a DJ. Okay, they wanted to become a DJ, but without spending 1,000 hours trying to see some tutorials on YouTube. And the thing is that actually, so it's very complex to become a DJ because you have to learn how to turn all these buttons and so on. But the thing is that for reservoir computing people, even if you're not expert, you just need to also turn some little button, and it's not so complex. And so, but we cannot interact with a reservoir like we do with a DJ table. So the idea is that can we just have this interaction, this loop with the environment, like changing the button and hearing what's the impact of it, as a reservoir. So the idea of the project was to play a reservoir like if it was an instrument. And so actually they won the hackathon because they had a simple idea that actually worked. I didn't thought it could work so easily. And so the idea as the beginning was to do go beyond classical arpeggiator, because if you do a bit of music by computer, you see that you know that when you do a chord on your keyboard, then you can do 2-2-2. It can go up, down, or up and down. But then after this, you don't have much things to do, and it's not so. You can create more complex things. So the idea is to try to create more complex arpeggiator, and that's the demo they had just after the hackathon 2 years ago. And I have to put the sound up. So you can see that he's just touching the chords and the reservoir is playing. But what I forgot to tell you, and which is very important, is that actually we didn't even train the last layer. So this is a purely random network, okay? So just random stuff, just random connection, and just putting the hands like this. So, and the fully random network just selects one note at each time, okay? And at some point, you will see it change some parameters. And it will change the melody. So this is the activity inside the random network. And so here it changed a parameter called spectral radius. We will see later what it is. And you hear that the sound is changed a bit. And you see on the dynamics of the network that also the dynamic has changed. On the Ableton Live setup, you can see different parameters. And this, now it's increasing a lot, making the network chaotic. You can see now that the activities are going around. And that the music even changed more than before. So did it seem random to you? Or a bit some kind of musical things? Okay, and now, so that's, so we were so surprised that it works so well, like that they continue studying it, they finished their PhD. And actually now they are doing INRIA Startup Studio in Bordeaux. They are to create a startup to create plugins for musical softwares with this. Okay, so you can look at Alendia online. So we saw that random networks, even untrained, can generate fascinating dynamics, and reservoir computing exploit this natural dynamics of random networks to learn, okay, to create interesting stuff. And you can see that, for example, this is the dynamics inside the reservoir, and they can be rich, as we saw in the video. And you can do stuff with it. Okay, so why is it called reservoir computing? So first, the name reservoir is the recurrent part, so just the middle part. The readout is for the output layer, so this part here. And so the idea is that you have a lot of computation, a lot of combination that are made inside the recurrent layer, thanks to the random projections. And the reservoir is literally a reservoir of computation, okay? And that's why it's called reservoir computing. And what is important here is that the reservoir is nonlinear. So you can make a lot of nonlinear computation. So you have rich computation, and then you just linearly decode with the readout the combination that will be useful for your problem, okay? So you have a pool of complex computation made by random projections. If you do the same in the same order, they will do the same, so they are deterministic, these random projections. And then you just have to select in this pool the areas of the pool that are interesting to you and to select this kind of computation, okay? So if you are familiar with the SVM, the support vector machine, it's a bit the same idea, but in the temporal fashion. So you go from a low-dimensional input space where you cannot separate the blue dots from the red dots, and you project it into a higher dimensional space where you can find a linear separation between your dots, okay? Okay, why are we talking about potatoes now? It's because when I cook potatoes, I try to be lazy, so I just do random movements from time to time, and for me it works. I don't know for you. But the problem is that if I'm too disturbed by my phone, then I tend to forget to make some movement, and then my potatoes burn. And if I drink too much coffee, then I try to mess a bit the kitchen. And so, so we see that in an everyday task, we can do random movement and it works, but it has to have this parameter of dynamic things. And these dynamic things, dynamic richness, it's a bit related to other principles in physics. For example, when you put water, when you heat water, you have different dynamics that are at different levels. And what we're interesting for reservoir computing is to be at the edge of chaos. So not too stable because nothing is happening here, and not too much like to have a control on it and to have interesting computation. And so this is called the edge of chaos or edge of stability. And so the idea is that all the things that I just talked about, so this edge of chaos or this moving potatoes, it's related to the spectral radius. So the spectral radius is just the scaling of the recurrent connection. So that's just one number. And if you look at the eigenvalues of the matrix, so I won't explain what are eigenvalues. We don't have time. So you just take the radius of the spectrum of the eigenvalue. Okay, so that's why it's called the spectrum radius. And so it's the highest eigenvalue in absolute value. And you see that if we take just, so we look at the activity xt across time inside the reservoir, what we did before in the video, and we look it for a spectral radius of 0.1. You see you have some fluctuation, but yeah, the water is not moving much, so nothing seems to happen very much. If you take a spectral radius of 1.25, then you see that you have water boiling and the potatoes are well cooked, and you see a lot of dynamics happening here. And if you take a spectral radius of 10, then you can see like the last dynamics we saw in the video, and you see that actually everything seems to mix, and you have sharp changes all the time, and that's when the water is boiling out of the, I don't remember the name for casserole. Whatever. Okay, so the idea is that with this scaling of spectral radius, you can choose, you can adapt the dynamics of the reservoir for each task that you need, depending on this. And this is just one number, that's why it's nice. So for example, if we take another metaphor, if the spectral radius is the fishes inside, if they are small, the water is not moving. And if they are too big, the water is going to mess around. And actually, is there other parameters that could be useful to tune the dynamics of the reservoir? Yes, there are other hyperparameters. So they are called hyperparameters, by the way, because they are not trained, they are not learned by the system. And for example, if you take some honey instead of water, then even if you have big fishes that would mess around, now they don't put honey all around, and this honey is called the leak rate. So it's the equivalent of an inverse of a time constant, and you see that it's changing depending on a low or high leak rate. You can see that it also slow down the dynamics and so on. So it's a bit like a battery. So if you charge, like for each neuron, it's its ability to charge or discharge rapidly, okay? And so this will compensate, this can compensate for the high spectral radius or low spectral radius, okay? So these two things, spectral radius and leak rate, are important parameters in reservoirs to control the dynamics, okay? And that's nearly all. There's only one or two other important parameters, but that's all you have to do to have good dynamics inside your... Yeah, I forgot to remove this. No, I'm kidding. So yeah, so basically I said that in the next slide I will show the equations of the reservoir, but now, if you listen to me carefully, you should already have a rough idea of how reservoir computing works, okay? So you don't need to see the equations to understand how it works. So this is just the update equation of the reservoir, so inside this one. And you can see that if we go into detail, we can see that it's not so complex. but that's not the aim here. And if you have some question, I can come back on it. But the idea is that the dynamics and why it works well is not inside the computations, okay? And that's and there's a reason why. It's, for example, because reservoir computing actually now there's a high trend on physical reservoir computing. That means that you can actually use physical media to do a reservoir. So, for example, light. You have the company Lighton that started its business with this. So, try to do computation with lasers, using physical properties. Or, for example, with magnetic properties. And now we have a PhD student share with INRAE Paris that starts to do a model of reservoir bacteria. So we try to see how to compute with bacteria, like Escherichia coli. So it sounds, I'm very excited by this idea. Okay, so let's get back into with our babies. Okay, so the idea at the beginning was to see how we can bootstrap, have this model, this bootstrapping. So we say that transformers are not very useful for this. So we'll try recurrent neural network, and namely reservoir computing, as I just showed you, and LSTM, long short-term memories that you probably know, which are another kind of recurrent neural network. And so we will train the model by cross-situation learning, so not supervised learning, but kind of similar things, but more ambiguous, because the baby don't see correct information all the time. And the idea is that we won't just learn one word at a time, but we want to learn the whole sentence at once, okay? So for example, we have the ball is orange and the orange is on the right. You have to imagine that the baby or the robot don't know anything, and it has different objects on the table like this, okay? And so we will try to have the model learn all the sentence, all the meaning of all words at the same time. And you have some specific things, but I can come back on it. It's not very interesting for now. And so we did actually this experiment with the Now robot with colleague in Hamburg. And that's the same idea as modeling. We use robot to model how the child could learn language. Okay, so we have a reservoir. And I say, for example, a simple sentence like the cup is on the right. And you see the dynamics like when I had this Garfield cartoon. So it creates dynamics inside. And on the other side, we have this robot that has, so we simulate the vision, and we say, okay, it perceives some object on the table. So for example, a cup and a packet of tissue. And then we represent them in a very easy way of easy representation. So we have a first object which is red on the right, and which is a cup. And the second object is blue on the left, and it's tissues. Okay, so we have this, and we want to use the vision to train this language model, okay? And the idea here is that, the problem is that here we have a lot, okay? We have cup right red, tissues left blue. So there's too much features compared to what's inside the sentence, okay? We just want here the model to output cup and right. But as we said, we want to imitate a bit how children learn. And that's why we do cross-situation learning. So even if it's in ambiguous teaching, at the end, the model should output the correct values. So just for this one, so after training, it should output cup and right, and not all of the irrelevant features that are not inside the sentence, okay? Okay, so as I said, we compare reservoir computing and LSTMs, which are already well-known recurrent neural networks that work well, but which has more complicated components. So each unit you have to train out a lot of parameters. So for the biological computation, it's not as good as reservoir. Okay, so once we train the system, so with just 1,000 sentences, so very, very, very few of them, and we have this long sentence on the right, there's a blue orange, and an orange cup is on the right. And so you can see there's orange 2 times, but once it's an object and once it's a color. So it's a noun or an adjective. And we didn't tell the models that some words could play different roles, okay? Could be of different categories. And we can see, if we look at the outputs of the reservoir, for the first object, we can see that for the object part, it's recognized that it's an orange, that it's on the position right, and that the color is blue. And if we look at the second object, we can see that actually it's a bit mistaking. So when we go on the right, there is a blue, orange, and an orange cup. Then it's making a mistake here because orange, it is thought as a noun first, so as an object. So it's predicting this, so as a human would expect actually. But then when it is cup, it's changing its prediction, okay? And then it predicts the other things well. And so all this happened on the fly, as our request at the beginning. So it means that we didn't say, okay, orange at this position means this, or whatever, blah, 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 blah. We just give the whole sentence, and we feed with the vision, what the vision sees. Okay. So the next slide is a bit complicated. There's a lot of results, but we are comparing the reservoir with the different version of LSTM of different sizes, okay? And we see that so this is the error, so the lower is better, and we are comparing the errors for an increasing size of vocabulary. So if for example, we start at 4 words, the system has just to learn 4 words, and you see that both models are very good, they have very low error rate. And so there's 2 valid and exact error. This is just how if I say you see, imagine a woman with an umbrella in the street. Which color is the umbrella? Maybe you have a color, maybe not, depends on how you represent stuff. But basically that's the difference between valid and exact error. If the umbrella is red, then it's just a valid error, and if the umbrella has no color, it's exact error, okay? Right, it's exact and valid. We can come back on this. But just what we have to see here is that for the reservoir, actually, the red and green, you can see that when we increase the size of the vocabulary, it's generalized very smoothly. So we still have 1,000 sentences, and even with a size of 50 words, the model is able to learn in cross-situational fashion. And if you take different model of LSTM, 20, 40, or 80 units, you can see that they don't scale as the reservoir, like they don't generalize as fast as the reservoir. Like they need more data to generalize. And when we compare, so the reservoir is 1,000 units, but untrained units, and the LSTM is 20 units. So these 2 models are equivalent in terms of number of weights, number of parameters that we train. Okay, that's why we compare these 2. And the others we just, okay. So it's very good. We have a reservoir that works well, and we also showed on different corpora, so more complex corpora like gold corpora, which is a corpus for robots and for symbol grounding learning and other kind of more complex robot data. And so now if we want to understand why reservoirs and LSTM work differently, we did some kind of investigation on the states of the system and did a UMAP, so that's a method to represent in 2D a compression of the high-dimensional space. And we see that for the reservoir, actually you have the space is widely populated. You can see that you have different sentences, each point is a part, is a state inside the reservoir. So you start at some point, like for example, you start here, and you go, for a long sentence, you have a long trajectory, or for a short sentence, you have a short trajectory, and it's different states. So you can see that the states are well distributed, And if we look at the LSTM, for example, the states are much more compressed, okay? And this is, so actually you need to much more precise things to see where the dynamic, how to learn with LSTM, okay? So that's probably why LSTM are not able to generate quickly with new words, okay? Because they need to see them a lot of time to really learn to expand this representation, like what the rich representation, like what we have in the reservoir. Okay, so an intermediate take-home message is that random projection enable to bootstrap language learning. So the reservoir starts from richer dynamics compared to LSTM, and they produce a richer input. So this is a pun of word on the poverty of stimulus hypothesis of Chomsky, which states that children don't have enough linguistic input to learn grammar. And so the hypothesis is that the reservoir creates input abstraction from scratch. And that's what we showed in this result. And it's also, we also have a coherent result with when you combine reservoir computing and reinforcement learning. I don't have time to show here, but we did, for example, on a task on sensory motor learning, so this is not on language, but where you have these problems where you've seen, where you have little agents have to learn to walk with different kind of bodies. And in different tasks, if we add the reservoir computing just as a pre-processing untrained before the reinforcement learning algorithm, we can have like 10 times faster training. Okay? And so this was published at EvoStar conference. Okay, so now the last part on the BrainGPT project. So the idea is to try to make hybrid models between reservoir and transformers. So to combine this richness of random projection with the very powerful attention mechanism, which is very nice in LSTMs, transformers, sorry. So to build model with less data and more biological insights. Okay, so we've seen before that transformers are not so good because they have to read all the time the book for each word they generate or they read, which leads to a quadratic computation. And so we want to adapt this to make less complexity. And so with my PhD student, Yanni Bendiwiz, on this BrainGPT project, he managed to find actually constant complexity per time step instead of n squared. So the idea is to do the same amount of calculation at each time step, regardless of the sequence length, okay? So regardless of the length of the book or your question. And so the idea is that we go from the transformer decoder architecture and we just change a few things and we add a working memory with previous state attention here in the loop, and we are able to break this quadratic computation like this, okay? So we have, so we integrate directly the memory inside. We avoid rereading the entire book. And so we have a fixed size storage memory buffer here. So of course, some information may be discarded, like other RNN. And what's interesting is that unlike other approaches that modify or replace the softmax, we keep the standard QKV, so the standard attention mechanism of transformers. And so the idea is that we use actually a fixed number of working memory units that are actually reservoirs and which actually maintain their hidden state, and they each output a state vector. And then the attention mechanism operates on the state vectors of all memory units at once, okay? And so as the number of state vectors is fixed, you have constant attention cost, and the complexity is then independent of the sequence length. And so I guess you understood, but this part is actually what is happening inside this working memory and self-attention. And one of the novelties is that actually we have an adaptive leak rate. So actually on the reservoir computing side, like each memory unit, as I said, act as a dynamical reservoir. And we actually here we learn the dynamics. Okay, so back inside the learning, each reservoir learns its own spectral radius. Okay, before it was a hyperparameter. Now it's a parameter because it is learned. And actually, we did a different test with the leak rate learn or adaptive leak rate. And actually, the best option is to have an adaptive leak rate mechanism that you can see here. Is that actually each unit has the ability to, you remember this battery effect? So actually, each reservoir can freeze its dynamic or make them very slow or happen very fast or slow, okay? So a bit like when you can gate information in LSTM. But this is, but here it's not at the scale of a neuron, but at the scale of the whole reservoir. And so each memory unit actually computes its leak rate given a score. So it's a bit, if you're familiar with the mixture of experts, it's a bit similar to having a mixture of experts here. Okay, so the advantages that now we enable online processing of sequences. It maintains rich dynamics through memory compression, and we preserve the standard QKV attention mechanism. And now we have a recurrent neural network transformer with memory, constant per time step complexity, and constant complexity instead of square. And so now, what about the performances? So we compare to a benchmark. That will be the two last slides. So we use a benchmark that was used from a lot of different data sets, Mamba and so on, and other model done by Wang and et al. And the idea is, here you have an excerpt of different tasks, and there's 69 tasks in 5 categories. And so I won't go into the details, but what is interesting is that actually for 2 of the categories, our eco-state transformer, like EST, that you can see here, perform best compared to a dozen of other models. So we are very happy of this because it was the first benchmark that we tested on it. And so in classification and anomaly detection, they are very good. So here, higher is better, but then, for example, in long-term forecasting, we are very bad. So then we have to still adapt some things or just use it in these cases, but this architecture is not good for all tasks. But as many architectures, they can work for different stuff. Okay, so this is the summary slide on the eco-state transformer. So we did a RNN transformer model a bit like Mamba, if you know. We have state-of-the-art performances on classification and anomaly detection. And we manage, so theoretically it's very interesting because we managed to hybrid reservoir computing and transformers, learning the spectral radius and having an adaptive leak rate mechanism. So of course we have some limitations. So training is limited so far by backpropagation through time. So as you like when you train LSTM, so it's costly to process, and they are not so good as we saw for some tasks. So the perspective now is to enhance the model by making it parallelizable, sequence-wise. So we won't need any backpropagation in this way, using linear reservoir and breaking the feedback loop to previous state attention. Then it will make much more faster to train. And with this, I want to thank you for your attention. And you have the preprint QR code if you want for the EST, and the QR code for reservoir planning as well.
Do you have questions
Online? No.
Okay, here. Any question?
Thank you for the presentation. if I understood well, in one of the comparison plots, you mentioned that the reservoir has 1,000 units, and the RNNs, they had like 20 or 10 units. So the model size or the amount of parameter in these two approaches are different, right? So
the idea here, so the idea here is that in the LSM you count all the weights because all the weights are counted, and this is equivalent when you have for this task when you take 20 units here, it's very equivalent of having 1,000 units inside the reservoir because only this one are computed. Because here, when you have just for the inside the recurrent layer, you do 20 by 20, you already have 400.
okay.
So that's why, and then with input layer and output layer, it goes similar to the reservoir task. Okay. But we compare also with, so even with more, that's why we also increase. So here, for 8 units, we still have more, so we have much more trained parameters here than inside the reservoir, but still, you can see that these curves, it's just, even if we go more and more, it will, but then, okay, we can say, okay, if we put 1,000 units, then maybe we can reach there. Well, maybe, but then what we will have? Would we have a LSTM or kind of reservoir LSTM that don't have time to train its own parameters? So in the end, we go to the same, for me, it goes in the same direction. So if you don't, untrained networks are already quite good to use.
And the other question is, the reason why this reservoir is so effective, I mean, comparing to an old architecture like this ResNet with these residual connections, I read that this residual connection serves like a potential architecture that it's not fixed. So in this case, when you have these randomly connected neurons, are similar to that? I mean, why this is so effective?
So the ResNet is for image. So the thing is that ResNet is a feed-forward network, and of course feed-forward and recurrent network don't train the same. So feed-forward network with backpropagation is very efficient to train because you can parallelize a lot. But the problem with recurrent system is that for LSTM or for the architecture that I showed in the end, you still have to use this backpropagation through time, and you have to compute at each time step go back in time for 100,000 time or whatever.
And the last question is regarding to the last model. One of the tasks is involved the first task that you mentioned, like
for the 5 tasks.
Yeah, for the last model, one of these tasks is associated with the cognitive process that you mentioned in the beginning.
So I'm not sure. So this task or the general task?
Using this model.
Yes.
Did you?
On the cross-situational learning. Yeah. No, we didn't have time to try it.
Okay.
So yeah, this model we finished it a few months ago. So, and now we're already trying to work on the next updated version to try to scale to language actually.
Thank you.
But yes, that would be, we will try at some point, but...
Hi, thank you for your presentation. In the long term, do you see there might be a risk while creating this working memory in terms of sensitive data or private data? Or would you just put on guardrails to secure that memory is not storing data that it's not supposed to be storing?
So I understand your question, but I would say that any you will have the same problem with any architecture because transformer you cannot, you take the whole data. So you have problem with the security data. So I don't know So I'm not sure how to understand or answer your question.
Because transformers, in the end, you still do need to read everything all
Yes.
at once
Yes.
to give an answer, but you wouldn't. You would store all that information. So you could also store sensitive data.
But like the transformer, no? So, tell me how would you do for your
or what's the
transformers, and maybe I
difference?
can say.
What's the difference between your working memory and the transformer?
So the transformer, you have to give the book at the whole sentence at once, and we give only one word at a time, or one token per token. So it's similar to a word, but not exactly. But so that's the difference. So we don't. So that's why we reach constant complexity.
Ah, okay.
And so this is just a state. So you don't have it's embedding representation. You don't have access to the words inside.
Okay.
So if I had to answer to your question, I would say that this is better because for the security, because you don't have to reprocess everything, and you can just store everything as a state and don't have access directly to all the past information.
Okay. You also mentioned that you trained the models with biological insights. That was in a slide. What do you mean by biological insights?
But just the fact that you... so we know that we learn from few data, like the children learn by bootstrapping and can go very fast in learning different steps. And we process, when I speak to you, I give only one word at a time, and you're able to understand everything, right? And so that's very different from having access to read the book at each second when I try to understand you, okay? As if I would have access to the whole discussion that we have at all time, which is not the case.
So it's just mimicking what we do, but it's not biological, actually.
We try to do biologically plausible model, but we don't. Then that depends what you want to ask by a biologically exact model, because we don't need a model has to be simpler than the reality. Otherwise, it's not a model. If you make a model that is as complex as the brain, like some European project did some years ago, then if you want to understand your model, it's as complex as understanding a brain, so you're not help.
Okay. And my final question, in your GitHub, we can access the model?
For this one, I think, so this one is still a preprint, so it's not accepted yet. So maybe we have a version which is anonymized, but we don't have the full GitHub yet. But soon. We will make it available as soon as it's published.
Thank you.
Hello. Thanks for the great talk. My question is, if you had all the computational resources, the data, and the team, which tasks or cognitive tasks do you think you could beat the latest model, like Gemini 3, Claude, and stuff in the next 2 years?
So for Gemini, Claude, and so on, we will have to have a model that scales a lot to be able to learn with much more data, as with
Suppose you have all the resources, all the same resources, the same
but
data.
The thing, as I showed in the beginning, it's not the same model that maybe can scale, like reservoir computing does not get to this kind of scale, for example. But it learns with small data. Like even us, we couldn't read all this and maintain all this information. But so actually, to compete, I think it would be interesting when you try to do understanding on the fly of audio. Like to try to translate on the fly or understand or react on the fly. All these systems, they kind of now try to interact with you, but for example, if we try to speak and be very fast in speaking, or much more practically when you are musicians, we play at the same time and we have to synchronize. So having this kind of architecture, being able to synchronize and understand each other at the same time would be on the fly would be a nice task.
Okay, thank you. And with the resources you do have now, what do you think you will achieve from here to 2 years next?
I think we can. I think we can achieve to have a model, this kind of hybrid model, like eco-state transformer or another kind of similar model, to be parallelizable and scale more to language. So we already have early result that shows that the new version of the model is scaling to language text and be able to generate text. So from a kind of GPT-1 version, but it's a first step. So we will see already in 1 year at the end of the PhD of Yanis how well it goes. Thank you for the questions.
Okay, there is a question online.
Yes?
It says, I'd like to ask if it has been studied whether the internal representations align with neural data, like what Couch did. I don't know if I said it well.
What is the name?
Couch. If you like, you can read it here.
Cache, okay, yeah, like, yeah, cache and genre making. Yeah, so Yanis is an expert in transformer and reservoir now, so it's doing the model. And of course, later we would like to try to have this similar experiment on brain prediction we did. But so far we need to have first the architecture and then we will compare. But still, we still want to do this at some point. But we will need someone that knows more brain, like a specialist, like it's really at the beginning. Okay, yeah, for this, yeah. So we already did some comparisons, but for pure reservoir computing, it doesn't scale to language model, so that's the problem. But as soon as we have models that start to scale as a small language model, we can do again this kind of computation. Yes.
Okay, thank you.
And I also have another version. So a model on the reservoir model that I did 10, 15 years ago. You actually have dynamics. So it's not you cannot decode the brain, but you have dynamics. For example, when you have a complex or ungrammatical sentence, you can see dynamics of the model that are kind of similar to what happens in our brain. Okay. So we already have, and that's why reservoir are interesting for this.
Thank you.
Thank you.
So I was wondering, how do you come up with the last model, that hybrid model? So did you take inspiration for, I don't know, cognitive models of kind of cognitive science for doing that? Or because there's a lot of work about cognitive architectures and that kind of things. So yeah, my question is, how do you plan to maybe extend this work also for different type of tasks, for scaling the type of tasks that you are kind of solve? And also, since it works well for online learning or on the edge, like robots or something, so do you plan also to kind of focus more on that part? Or, I mean, at the end, what is your end goal for kind of having a model a language model for doing certain tasks, or trying to understand the brain better, or a mix of things, or I don't know?
Okay, so I try to answer to the different questions. Yeah. So the first question, where does the inspiration come from? So the motivation is biological plausibility and this on-the-fly and bootstrapping mechanism, as I said. But for this architecture, how it works, it's really on the mechanism of the transformer and reservoir, how to combine the two. So we did already a previous architecture called RAN that wasn't working as well as this one, so which was actually kind of a transformer inside the reservoir. And now we try the other way around, so to put reservoir inside a transformer, and it seems to work better, or at least how we did it. And it seems that this reservoir inside transformer, it seems to be interesting. And in parallel to what I said, I think reservoir computing in general could be more used in a lot of tasks or in a lot of architectures because it's kind of a bootstrapping ability or random projection can be used, for example, with reinforcement learning, as I said before.
Yeah, because for instance, in cognitive architectures, you could have different type of memories also, like working memory or maybe long-term memory or episodic memory. So maybe there's some inspiration that you could take from there.
Yeah.
And also, I saw a lot of works with reinforcement learning that. So yeah.
Yeah, but so I don't have the slide here. But so the biological inspiration also maybe, if I understand your question in another way, is that actually the idea of reservoir computing, it's to do a generic computation. So to do what we believe a cortical column, so just one part of a cortex, is doing. So it's that the ability to do generic computation and to adapt to different parts. So if you have a cortex here, it's for vision. If you have cortex here, it's more for syntax and language. So so the idea is to do a generic computation which works which is biologically plausible. And of course, and that's why reservoir computing I didn't say, but it came from both machine learning and computational neuroscience side. And then for the application, that was your question?
No, I mean, at the end, what your end goal is to focus more on the edge, or maybe your online learning to kind of build a model for solving certain tasks, or is maybe focusing on like understanding the brain, or kind of having a model that human inspired can solve certain tasks.
So I think I have several goals. So one is more on what I just showed here, like more fundamental, to try to understand this learning mechanism and compare to what could happen in the brain. Then also some applications, so make reservoir computing more popular than it is now. So because it's not purely deep learning, then not a lot of people are pushing for it, but it should be better known. That's what we do at Reservoir Pi. Then I also want to understand better how the sequences, like bird song or language, are processed inside the brain. So that we did also experiment like this. And I work also with canaries to try to understand, for example, how they learn their syntax. And I have an engineer also actually I have two engineers starting to try to understand how canaries are able to generate all these complex grammars within the song, and how we have also neural data of canaries to try to see how this syntax is coded with real neural activity. So that we probably won't have at this level for humans. And the last one is try to do some kind of application. So use this in real-time applications like music or like robot interacting in real time in a conversation.
Okay, thank you.
Okay. So thank you for all your questions. That was very nice. Thank you for doing.
Yes, so it was more for the people here, but thank you all for listening, and thank you, Xavier, for this talk with good questions as well. So thank you so much.